All right, so this video is about bounds of the zeros of polynomials. And so this is the theorem itself. Let f of x be a polynomial with real coefficients, a positive lead coefficient, and degree n is greater than or equal to 1. Let a be a negative number, and let b be a positive number. So that's just part of us defining and setting up, and here's the actual statement of the theorem. No real zero of f is greater than b if the last row of synthetic division of f by x minus b contains no negative numbers. Okay, so what that means is we would call b an upper bound of the zeros of f if, when we did synthetic division, that's the polynomial we're going to be playing with. So let's say I did 2, negative 14, 2, and 12, and I divided it by 32, right, x minus 32, and 2 multiplied it, got some very large number, and we got all these big numbers. 26. These aren't the correct numbers. I'm just writing something down. 1,800, 6,062. So notice how all of these numbers are positive. I'm just trying to give you a visualization. All of these values are positive. So all those numbers are positive. That means 32 is an upper bound. By the way, 32 is in fact an upper bound of this polynomial. These are not the correct coefficients after doing synthetic division with it. I just didn't want to spend the time doing the math, nor do you want to watch me do arithmetic. Okay? So that's how you determine whether a number is an upper bound. If all the coefficients in the final row of synthetic division, so the coefficients of your quotient and the remainder, if they're positive, then it is an upper bound. The other side, if you take a negative number, so no real zeros, no real zero of f is less than a, remember a was a negative number, and we call it a lower bound if the last row synthetic division of f by x minus a has entries that alternate in sign. 0 can count as positive or negative. So again, if I tried negative 16, let's say negative 16, and I divided it into, these again are not going to be the right coefficients. They're just made up coefficients. This is going to be what, negative 32, and this is going to be negative 34. And this is going to be some negative number times some negative number. But 16 times 34 is some large 762. It's not 762, but whatever. 856, I don't know. Whatever. And it's going to be some large number. If it was 856, then it'd be that. And then it's going to be a large negative number. That's going to be a large negative number. And then negative times negative is positive. It's going to be like positive 6,756 or whatever. 60,756. Some large positive number. But more importantly, we can notice that it goes from positive to negative, negative to positive, positive to negative, and negative back to positive. So the signs, SIGNs, are alternating. That means negative 16 is a lower bound of the zeros. So what does that mean? I now know that negative 16, by the way, negative 16 is a lower bound. And this is kind of a conceptual thing. Negative 16 is a lower bound and 32 is an upper bound. That means my zeros are between these two values. The zeros of my polynomials are between those values. Don't even have to do anything else. I know that they're between them. Now, if we did our p's and q's, which we are going to do for this polynomial, the p's over q's, we're going to see that the real zeros aren't possibly negative 16 and 32, just examples. Here's a bigger idea. If negative 16 is a lower bound, certainly negative 17 is a lower bound, and negative 18 is a lower bound. So how many lower bounds are there for a polynomial? Well, there are infinitely many. So negative 16 is, but every number less than that will also be bounding them. In fact, negative 16 is not the greatest upper bound. It's just greatest lower bound. It is just one of the many, infinitely many lower bounds. It's kind of important for us to find the greatest upper bound because we want to know exactly where our zeros are in between, or as best we can, because that helps us to find or narrow down our list of numbers with which we have to do synthetic division with. And we're going to do that with this example. Same thing, we want to find the least upper bound because 3,062 is an upper bound. If 32 is, so is that one. But 3,062 being an upper bound doesn't help us at all because there's still way too many numbers in between negative 16 and 3,062. So one of the first things we want to do, as Descartes showed us, is take our infinitely many list of x's and narrow that list down, at least for the real possible zeros. and we find our p's. Remember, the p's are the factors of 12. So it's a set of numbers plus or minus 1, plus or minus 12, plus or minus 2, plus or minus 6, plus or minus 3, plus or minus 4, and that's it. Our q's are the factors of the lead coefficient. In this case, it's plus or minus 1 and plus or minus 2. And then our p's over q's are the set of numbers that is the ratio of all the possible p's in their combinations with all the possible q's. When I divide all those p's divided by 1 or negative 1, I'm going to get that same list. So I get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. And then when I divide all of these numbers by plus or minus 2, I get plus or minus 1 over 2, plus or minus 2 over 2, but 2 over 2 is just 1, and so that's repetitive. I'm not going to write it down. You can, if you want, and clean up your list later. It's up to you. 3 over 2 is plus or minus 3 halves, which is a new number in our list. Plus or minus 3 halves. And then 4 over 2 is 2, 6 over 2 is 3, 12 over 2 is 6, and we have all those numbers represented there. So our list is complete. Oops. Now I have those, 1, 2, 3, 4, 5, 6, 7, 8. 8 pairs of numbers, so I have 16 numbers to choose from. Now I've listed those numbers on the number line. It's not to scale, it's just to give you an idea of where those numbers sit in relation to each other. Gives you a visual. Now, I could choose 12 and to see if 12 is an upper bound. But I would tell you it's not very useful because I know that my possible real roots are not going to be greater than 12 anyway. So why would I start there? I don't eliminate anything. If I just want to try them all, yeah, sure, start with 12. But I want to eliminate some numbers. So I'm going to try 4. And if that matches up, if 4 is an upper bound, well, 6 is an upper bound, 12 is an upper bound, and I don't have to test them. I already know that they're going to be upper bounds if 4 is an upper bound. Why did I choose 4? Well, it's approximately halfway between our values. It's not exactly because it's half. 1, 2, 3, 4. 3. Between 2 and 3 is halfway. But if I get overambitious, I could go down and try 1, and if it doesn't work, I don't find my bounds. I might find a 0. So there are 2 different contexts in which you're doing this. One, the contrived problem, where you're just trying to find the bounds, but that exists to practice finding the bounds and understanding the idea of the bounds. In the real sense, what we want to do is use this when we're solving polynomial equations, or finding the zeros, roots, or x-intercepts of said polynomials. So we're going to try 4. We'll do this little synthetic division. What are the coefficients of my polynomial? That's the blue thing. 2, negative 14. So 2, negative 14. I think it was 2 and 12. Yep, positive 2 and positive 12. So remember, in synthetic division, I'm going to break down the first coefficient. I'm going to multiply times 4. So I'm going to get 2 times 4 is 8. I'm going to add, so 8 plus negative 2 is 6. 4 times 6 is 24. I'm going to add the negative 14 and get 10. 4 times 10 is 40. Add the 2, get 42. 4 times 42 is 8, 16, 168. And so what do I get? 180. And so notice that all of the coefficients are positive, including the remainder, which is 180. So since they're all positive, then 4 is an upper bound. Now, is it my least upper bound? I don't know. What's the next number to try? 3. So let's try 3. If it becomes an upper bound, then 4 is not my least. So 3, what was it? 2, negative 14, 2, and 12. Let's go check. Yep. And then I'm going to bring the 2 down. 2 times 3 is 6. Subtract that, I get 4. 3 times 4 is 12. Subtract that, I get negative 2. That's negative 6. I get negative 4. 3 times negative 4 is negative 12. And in fact, 3 is a 0. So 3 is a 0. That's great. Depending on the problem, if you're trying to find the bounds, you just found out that the 4 was the least upper bound. 4 is the least upper bound. And Yeah, 4 is the least upper bound. But we also happen to find that x minus 3 is a factor, and that once I do that division, I have 2x cubed plus 4x squared minus 2x minus 4. So actually I have a new polynomial. So let's split this off into two different things. Let's finish finding the greatest upper bound of this polynomial. And we can try, let's try negative, well, I tried 4 before, and I suggested that 3 is actually closer to the middle, so let's try negative 3. So we'll try negative 3, and what was it? 2, negative 14, 2, and 12. 2, it's negative 6, that's negative 8. Negative times negative is positive, 3 times 8 is 24. Now I'm going to get 10. So far they're alternating, negative 30, so that's negative 28, still alternating. Negative times negative is positive, so 3 times 30 is 90, so that's going to be 84, I want to say. Or 80 something, I don't know. It's messing me up. I'm trying to do too many things at once. 28 times 3, 24. 2, 6, 7, 8. Yep, 84. And then I'm going to add the 12, and I'm going to get some larger positive number, which is 96. And so notice how it's alternating, right? This is positive, that's negative, that's positive, that's negative, that's positive. So negative 3 is a lower bound. It is not a 0, but it's a lower bound. So what do we want to try next? Possibly let's try negative 2. So again, we're dividing into 2, negative 14, 2, and 12. And so we get 2, so that's negative 4, negative 6, excuse me, and that's going to be 12. That's negative 2. So it's already not working, right? So negative 2 is not a lower bound. So we found our two bounds. Negative 3 is the greatest lower bound, and 4 was our least upper bound. If we finish this off, we're going to get 6. 2 times negative 6 is negative 12. We actually find that negative 2 is a 0. But since we know that that's a 0 from, remember I said we're going to split it into two different problems? We just finished the whole, what are the bounds of these zeros? And that's a different problem. So now let's move forward. We just had a hint because we're doing two problems at once. But if we were finding the zeros, I would have tried negative 3, which would have told me that I do not have to try negative 12, negative 6, or negative 4, because negative 3 was a lower bound. So I have these numbers to choose from. Remember, we determined that 3 was a 0. So we only have those numbers left. In fact, we probably have fewer numbers left, because this was my polynomial that I shifted to. So let's take this, x minus 3, and what was it, 2x cubed plus 4, negative 2, negative 4. 4, negative 2, negative 4. So that's x. This is x squared. That's where we were at. And so if you wanted to, you could do one of two things, right? You can find p's over q's for this new polynomial, which is going to be plus or minus 1, plus or minus 2, plus or minus 4, over plus or minus 1, plus or minus 2. And notice that I get the same list. And when I divide these all by 2, 4 over 2 is 2, 2 over 2 is 1, and I just get that plus or minus 1/2 as a possible. So that's my shortened list. So notice how 3 doesn't even show up anymore, and negative 3 doesn't either. We do know that negative 2 works because of our artificial doubling of the problem. So why don't we just go there? Negative 2 divided into this, 2, 4, negative 2, negative 4. And so bring the 2 down, I get negative 4, that's 0. Negative 2 is 0, negative 2, that becomes 4, that's 0. And I get x minus 3, which was brought down from here. I have a new factor, which is x plus 2. And then what's left over? 2x squared minus 2, because 0x. Now I'm going to factor a 2 from this. And get x squared minus 1, and that's a difference of squares. And if you don't recognize it, that's okay. Factor it. If you're not okay with factoring it, then you could use the quadratic formula. And we just finished the polynomial. So we actually was trying to demonstrate two things. Why does this thing exist? Cuts our list down. And then also the shear problem where I just need to find the bounds of my zeros. So hopefully this is helpful.